Welcome back. In this video, we're going to be talking about simplifying radicals. Okay, so in order to understand simplifying radicals, we have to know what a radical is. Okay, and you've all hopefully seen it and heard of it. The radical function is the most typically used example is a square root. So it's going to be this function here. And it does qualify as a function because it is a map from one set of numbers to another set of numbers. Okay? So it is a function. And in this radical term, there's a little bridge over here in the denotation. And if you put your math glasses on and you're looking at a square root, what you're going to see is a little tiny 2 there. Okay, that denotes a square root. Okay, and what it does, the square root is the inverse of a squared function or an x squared. Okay, so these two guys, the squared function and the square root, are inverse or opposites. They undo each other. So if you happen to have a square root of x squared, what comes out at the end, because the square root here and the squared term undo each other, they're opposites, what comes out is just x. Okay. Now, for the purpose of simplifying and letting you know the actual notation, anytime you see just this guy here, that's going to be an understood square root. And if you want to talk about a cube root, or the hat with the little 3 there, okay, that's going to undo, it's going to be the inverse of a cube function, or an x cubed. Okay. So, now that we know what a radical is, what the function is, let's talk about how we can simplify that guy down, okay? Because you can have all kinds of square roots. We know, for example, that the square root of 49 is 7, or the square root of 4 is 2, or that the square root of 9 is 3. Okay. But what if we don't have a perfect square in here? What if instead of 9 or 4 or 49 or 64 or 144, we put 8? Well, 8 doesn't really have a square root. It's somewhere between 2 and 3. Okay, so it's going to be 2 point something 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 long decimal. Okay, so we want to look at this in a simpler form. And that's where prime factorization is going to come in. I want to represent 8 in the smallest prime numbers multiplied by each other. So let's use a factor tree to get here. Okay, let's make a factor tree of 8 and see what its prime factors are. So if I start with 2, since I know 8 is even, I know I can divide it by 2, the other number that comes out over here is going to be 4. Okay, and let's continue the tree until we get the prime factorization, or all prime numbers down the bottom here. So 4 is going to be 2 times 2. And I'm done. I know that 2 is a prime number. So my prime factorization for 8 is going to be 8 equals 2 times 2 times 2. Okay. So since we know that these two things are equal, these two expressions are the same, we can trade 8 under the radical for 2 times 2 times 2. And once we make that trade, the key component here for radicals is, especially for the square root, is that we can find pairs here, pairs of the same number multiplied together, and take them outside the radical. Okay, it's like 2 people going on a date. Okay, you don't go on a date by yourself, you go in pairs, and you leave together. So once we find that pair of 2 numbers that are the same multiplied together under the radical, they can come outside the house, okay, the radical, and whatever's left inside this lonely 2 here, he gets left behind. Okay, so our simplified version of the square root of 8 is going to be 2 times the square root of 2. And that's also sometimes said as 2 square roots of 2. Okay? So let's take a look at another example. What if we had the square root of 48? Well, I know that 48 has a prime factorization of 4 and 7, 2 and 2. So that's going to be 2 times 2 times 7. And we'll see again that our pair is 2, and it's going to come outside. Okay, so that's going to leave us with 2 times the square root of 7. And it's that simple.